So let's go to the last one, which is the thickest. So again, the thickest is another timer application for Mbed, in Mbed, that is used for actually repeated timeout. Means that it's give you interrupt in repeatedly interrupt, or in period of time, always repeat. So let's look at the example. So the how to use is actually the same as the timeout. You see, the function is the same. Only the name is tickers. The previous one is the name is timeout. All right. So let's see this example. All right. So we can copy this to the Mbed simulator. But before that, let's see what program, how the program is executed. All right. Again, so we have the main program here, the main loop. Okay. So use the attach also timeout is the name. So here, because we declare the tickers as timeout, so timeout dot attach, and the name for the function, again, when we use tickers or timeout, you need to attach the function. Means that after the time is up, what you want the microcontroller to do. Okay, so in this case, after 0.2 second, we want the microcontroller do this. So LED switch. So this is the function. So what is that function? So this is the function. So the LED switch is actually toggle the LED, and the main loop is here. The main loop is do nothing. Do nothing. So when we run in our Mbed simulator, okay, go back to Mbed simulator. Okay, so in the Mbed simulator, one thing I want you to know is that you cannot have the while one loop and leave it blank like this. In actual hardware, it's okay, but in simulator, it's not okay. All right, so you need to have, you do something here. For example, you have wait function 10 seconds is done. Because if you don't have this, when you run, it will wait forever. All right, it will crash. So you can have a wait function here. What we want to do is actually we want to turn on the LED every 0.2 second. In this case, something like this also actually. So let's change to LED, maybe LED number 3, so that we can see this one turn on every 0.2 second, right? So run the program. See, so even on and off every 0.2 second, because we use tickers here. All right, when we use timeout, it will do this only one time. But if you use tickers, it will repeat. So again, you see, although you have the wait function 10 second here, okay, although you have function 10 second here, it will give you almost unaffected, right? Because every timeout, every 0.2 second, it will need to do this. Okay, toggle the LED every 0.2 second. Although your microprocessor is actually processing this and do the counting. All right. So while it do the counting, when the time is up, it need to go to this very fast, turn on or off here very fast. All right, and go back to do this. So, but if you're not doing, not using the hardware timer, for example, we want to implement this application and we have the wait function here without using a timeout, for example, right? So let's see what happened. So now we don't have, for example, we don't have this. We don't have this, and we don't have this. Our program is just toggle the LED every 0.2 second using the software timer. Hit 0.2. Yeah, right? And because we have this, right? And you see what happened when you run. Something wrong. Where is it? Closing bracket. On. Oh, yeah. Because of this, right? Run. Okay, should be good. You see, because now the microprocessor is processing this, executing this, do the counting 10 seconds. So it will not do this again. When you do this, it will go to wait 10 seconds, and the microprocessor is processing the wait 10 seconds. All right, again. So means that here your program, instead of flash the LED every 0.2 second, now it will flash your LED every 10.2 second. All right. Okay, so that is the problem when we use software timing, and we have many timing in our program. So instead of doing that, let's make this in using the wait 0.2 second. We use this hardware timer so that it will run independently from this. Okay, so you can move this and use this as the hardware timer like this. Okay. So here now this is hardware timer already, because you time off is now you attach to the tickers. This tickers is the hardware timer, and we will call this LED switch function every 0.2 second. See, so whenever you run here the microcontroller executing this wait 10, so but every 0.2 second it will go to this function and do this very fast, such that you cannot notice actually. Okay, so let's run. Okay, all right. Although your microcontroller is actually do the counting here, but at the same time it will check for the time out here, the tickers. So every 0.2 second it will do this. All right. So in this case also, by using the tickers, for example, we want to have two LED that flashing at different time. For example, let's say now we want to have LED number this LED 2 to flash. This one is 0.2. So let's say this one is to flash every 0.4 second. How to do that? So anyone with computer can do together. Yeah. So let's say the problem is this. We have this. All right. We know how to do this. Okay. Now we add another LED. So that LED, this LED is flashing every 0.4 second, for example. Or we have another LCD flashing 0.6 second, and so on. So let's see how to do that. So maybe we have another function. This is function 1. So we have the second function called switch LED switch 2, and this is time out number 1. So you can have another time tickers, but make sure that the name is different. So here you have two tickers, right? This is tickers number 1. So tickers number 1, let's say this tickers number 1 is for 0.2 second flashing, and tickers number 2 is 0.4 second. All right, and zero timeout number 1 is LED 3. So let's say we change to LED 1. This one is LED 2, and my LED 1, my LED 2. Okay, the name must be different, remember. And of course, you need to have another function. Yeah. Okay, this is function number 1, switch 1. All right, switch 1, and then function number switch 1 is for my LED 1. This one is for my LED 1. Switch 2 is for LED 2. This one is for LED 2. My LED 2. So it should be done. So here, now the most important thing is that we need to attach the tickers to the function. So the first one is time up and LED switch 1. This one is time up 2, LED switch 2, and run for 0.4 second. Okay, anything else? No. All right, so we now have two LEDs flashing. All right, LED 1 and LED 2. LED where LED 1 flashing every 0.2 second, and LED 2 flashing in every 0.4 second. And see what happened when we run the program. Okay, so we can see already this one is running. Yeah, here is 0.2 every 0.2 second, and this one is every 0.4 second. So you can always have up to you can have many tickers, yeah, and by theory is unlimited. By theory is unlimited. All right. Okay, any questions so far? Another 5 minutes. I need to finish this within 5 minutes. Okay, if no question, so let's do this a little bit more so that we finish all this. Okay. Tickers, I think done. The real-time clock, so you can use the real-time clock, and it is free. Yeah, means that it is built in the Mbed microcontroller. Actually, in the LPC 1768 microcontroller. All right, so the Mbed is one of the LPC 1768. So you can use it. It is run by another independent clock oscillator, 32 kilohertz oscillator, and independent battery supply. Means that when you power off your microcontroller, it is still running independently using internal battery. All right. So it will keep track the real time clock, real time, real time date, real time year. All right, so you can use that. So how to use this, you can check in the Mbed website. Actually, I don't have the example here. All right, the last one, this is the last already. Switch debouncing. So what is switch debouncing? Switch debouncing is the problem that, or issues that hardware designer will face most of the time. And when you deal with mechanical hardware like switch, actually when you press the button, in ideal case, when we look at the oscilloscope, we hope something like this, right? This is where when switch is not pressed, all right, 0 volt, and when we press, we hope that the response or the signal is very nicely changed from 0 to 1, all right? But in reality, all right, but in reality, because the switch is a mechanical switch, when you look carefully in the oscilloscope, all right, when you press the button, actually you have some kind of noise like this before the signal going to the stable state like this, all right? So this we call switch bouncing, switch bounce, all right? It looks like it's on and off many times already. So for example, you write the program. When you write the program, let's say you say that when this signal is equal to 1, you do this, all right? Or for example, you want to count, all right? When the signal is 1, you press 1 time means that you count 1 time. So, but in reality, when you in your simulation, it look good, right? You get the result, a very nice result. You press 1 and your display, your output is display very nice one. Press second time is display 2. Third time is display 3. Good. But when you download your program to the actual hardware and you connect to the switch, when you start to run your program, all right, you press, although you press 1 time, because of this thing, what happened is that, you see how many going up and down already. So your program, because your microcontroller will run very fast, it will always manage to count how many going up and down here, all right? It looks like you press many times already, although you press only 1 time. Okay, so this one is 1 going down, 2 going down, 3 going down, 4, although you press 1 time, because of this bouncing signal, means that your microcontroller will give you 4, or you start to worry already. Why my program in the simulation is work perfectly, all right, is working perfectly, but in the actual hardware, you get the wrong result. So because of hardware is not that ideal, and one of the issue is switch debouncing. So when you're working with hardware, and in the future also, because the next semester, next year, you will take final year project, right? You will work with hardware, and I'm not sure whether next semester you can do the hardware or not, because maybe most probably, not most probably, is yes already, that next semester you need to do your final year project using simulation only, right? You cannot use the hardware. Or maybe you, if you can buy your own hardware, then that is different issue, but you cannot go to the lab because of the this coronavirus problem. Okay, but just remember that when you use hardware, when you deal with hardware, this thing happen. All right. So how to avoid it, or how to minimize this effect? So what you need to do is, one more thing. One first thing is, you can do in there are 2 solutions actually. First thing is, you can use or write your program carefully such that it can eliminate or detect, or what do we call, identify this thing, all right? Or second thing is, you use hardware. You design your hardware properly by connecting your switch to the filter or the capacitor, so that the response time for this one, you have the parallel the switch with your the capacitor, so that this one is not sharp like this. Instead, it will go from 0 to 1 very slowly, all right, not very fast like this, slowly to 1 by using the capacitor, all right. That is by using hardware, but you can use software also by writing your program such that your program, when it changes in button, for example, you use interrupt, so maybe you need to write extra code such that you check again if this thing is not stable yet, means that you check, okay, interrupt coming, okay, you go to the interrupt service routine, okay, here, but in the interrupt service routine you check again, for example, you have a delay, for example, in 100 millisecond. If after 100 millisecond the signal here, the input signal here is still 1, means that that is the correct input, all right. But if after 100 millisecond it go down already, means that that is a noise only, all right. So you need to have an extra code segment that can identify this thing. And the best thing is to use delay, all right, means that whenever you detect this, you delay a little bit, 100 millisecond, for example, and you check again whether the input is still high or not. If not high, means that that is a false signal, all right. But if it's still high, means that that is the correct input and you need to respond to that, all right. So that is the solution. Okay, so here the solution is, the example of the solution is here, so you can actually go check here, right? Okay, but the idea is that, all right. So, all right, any questions so far? We actually officially finished already. So this is the last slide of the very last slide of this course already. All right. So yes, this course come to an end already. So here is the exercise. So you can try to answer the exercise. So there are many questions, 13 questions, and also the exercise for the serial communication. Okay, thank you very much.